Hi there, welcome to my talk. The title of my talk is Associative Submanifolds of the Berger Space, and it's based on joint work with Jesse Madnick. So the paper is also called Associative Submanifolds of the Berger Space, came out about 2 years ago, immediately just as the pandemic was hitting. So I'll begin by just explaining the plan for the talk. We want to study associative submanifolds of the Berger space. So we need to explain what are associative submanifolds and then also what are the Berger space before we can really talk about the results. So I'll begin by explaining what associative submanifolds are, and to talk about those, we need to talk about the group G2 and a little bit of stuff about nearly parallel G2 structures and their relationship to the theory of exceptional holonomy. So I'll begin with that, and then I'll give the background about the Berger space itself. So the Berger space is a particular example of a submanifold that has a nearly parallel G2 structure, and it has some other interesting properties that I'll explain in that part of the talk. And then, as should be clear from the title, we want to study associative submanifolds of the Berger space, and we do that by restricting to two particularly interesting situations. So the first situation will be the case when our associative submanifold is ruled by some special class of curves in the Berger space. I'll explain what those types of curves are in part 3 of the talk, and I'll also explain the result that we get about those. And then our second condition is we'll study associative submanifolds of the Berger space that have a so-called special Gauss map. And I'll also explain what that notion is and what our result is in this section of the talk. Okay, so let's go ahead and begin by talking about the group G2. So the octonions are an 8-dimensional norm division algebra. Because they're a norm division algebra, they have a sort of a unit element, which we can call 1. And we can form the imaginary octonions by taking the orthogonal complement of that one-dimensional space spanned by the unit element. So we can identify R7 with this space of imaginary octonions. And then on this copy of R7, we can construct a 3-form phi0 in the following way by saying, what does phi0 do to 3 vectors u, v, and w? Well, you just take the inner product of u with the imaginary part of the octonion product of v and w. So it's not immediately clear that this defines a 3-form because this formula only looks to be alternating in v and w, but it turns out, you can do some calculations, it turns out that this is also alternating in, say, u and v as well. So this formula really does define a 3-form. Okay, and then somehow the most simple definition of G2 is that it's simply the GL7 stabilizer of this 3-form on R7. Okay, so the group GL7 acts on the space of 3-forms by pullback, say, and we have this special element phi0, and we'll just define G2 to be consist of the 7x7 matrices, which leave phi0 fixed under this pullback action. Okay, so this is a nice definition of G2. It's not immediately obvious the following facts from this, but it's possible to prove then that G2 is a compact, simple Lie group of dimension 14. So in particular, we're talking about the compact version of G2 in this talk. Okay, now we can say a little bit more about G2. So the action of G2 on R7 fixes a positive definite inner product G, an associated volume form, which I'll call vol, which should be also the volume form of G. And these objects are actually defined by this equation that says that G of uv times vol, so this should be a 7-form on the left-hand side, that should be equal to take u and hook it into phi0, wedge that with v hooked into phi0, and wedge that with phi0. So that object on the right-hand side, that's a 7-form because u hook phi0 is a 2-form, v hook phi0 is a 2-form, and phi0 itself is a 3-form. So the thing on the right-hand side is a 7-form. And the claim is that you can write that as G of uv times the volume form. And you'll find, and if you do this, if you assume that vol is the volume form associated to G, this really fixes the scaling involved, and you really do get 2 well-defined objects. Okay. You would have to check, say, that the G here is positive definite, but it turns out that it is, you can do this in coordinates. Okay, well, it follows from this then that G2 should be a subgroup of S07, because if G2 fixes phi0, then it must also fix the objects that we define using phi0, and we've defined G and the volume form using phi0 only. So G must also preserve these things. So actually it turns out that G2 is a subgroup of S07. Okay, not, we said G2 was compact, so it would have had to be a subgroup of O7, but it turns out it's actually a subgroup of S07. Okay, so it's kind of a really quick introduction to what the group G2 is. And we'll go immediately now from this linear algebra in R7 to the setting of 7-manifold M. So in the same way that we define a Riemannian manifold to be a manifold that has a positive definite inner product at each point, we're going to define a G2 structure to be a 7-manifold that has a 3-form phi that at each point looks like the 3-form phi 0 on R7. So say we can always at a point pick a coframe in which our 3-form phi on the manifold looks exactly like the 3-form phi 0 on R7 that we just defined using the imaginary octonions. Okay, so we've transplanted the linear algebra that's happening on R7 to the setting of a sort of 7-manifold M. Okay, and just as before, the 3-form on R7 give us a positive definite inner product and a volume form. Well, if you use the same formula using a G2 structure on a 7-manifold, you'll get a Riemannian metric, which we'll call G phi, and a volume form, which we'll call, say, vol phi on M. Okay. Now, the topological condition for a 7-manifold to admit a G2 structure is relatively weak, I would say. The only things that are required are that the manifold be orientable, and that's clear because the G2 structure induces a volume form. And it's also required that the manifold be spinnable, so it has to admit a spin structure. So this is the vanishing of the first and second Stiefel-Whitney classes. The fact the manifold has to be spinnable is not, say, immediately obvious, but you can see it by realizing that the group G2 is the stabilizer of a non-zero spinner in the spin representation of SO7, the spin representation in 7 dimensions. So if you have a G2 structure, it turns out that you have a non-vanishing spinner on your manifold, so it makes sense that your manifold should be spinnable. In that case, should admit a spin structure. Okay, so the condition to admit just a general G2 structure is, as I say, fairly weak, but there are special classes of G2 structures which are particularly interesting. And the class that we're interested in this talk is the class of nearly parallel G2 structures. So we'll say that a G2 structure phi is nearly parallel if when you take the exterior derivative of the 3-form phi, you get 4 times the Hodge star of phi itself. So phi admits, phi defines a metric and a volume form, so those together give you a Hodge star, and we can certainly form the 4 form, which would be the Hodge star of phi itself. And we'll call it nearly parallel if it so happens that this 4 form that you get lines up with the exterior derivative of the 3-form phi. Now this is a nonlinear equation because to get the metric and the volume forms from phi requires doing some nonlinear operations, and then getting the Hodge star, you could do more nonlinear operations. So this object on the right-hand side is sort of a nonlinear combination involving phi. So this equation is asking a G2 structure to be nearly parallel is a nonlinear requirement. Okay. Now, why study these things? Well, the main motivation, I would say, comes from this theory of holonomy groups of Riemannian manifolds. So nearly parallel G2 manifolds are sort of, the best way to think of them is sort of models for conically singular manifolds that have holonomy group spin 7. So spin 7 is one of the exceptional holonomy groups that happens in dimension 8. So you can have an 8 manifold that has a holonomy group spin 7. And then in the theory of exceptional holonomy, it's often interesting, particularly because of applications to physics, you're often interested in singular manifolds that have exceptional holonomy groups. And so the simplest sort of kind of singularity that you can have would be a conical singularity. And then you ask, okay, if I have a conical singularity, what is sort of the link of the singularity look like? And roughly speaking, it should look like a nearly parallel G2 manifold. And that's because of the following theorem. So an 8-dimensional Riemannian cone manifold. So I'll say that cone manifold should topologically be a 7-manifold M times the positive real numbers, with the cone metric GC, C for cone, is equal to dt squared. So t should be the coordinate on the r plus direction. GC is dt squared plus t squared gm, where m is some metric on the 7-dimensional link of the cone. Well, this cone has holonomy contained in spin 7 if and only if your 7-manifold M admits a nearly parallel G2 structure and the metric on the link of the cone is really equal to the metric induced by that nearly parallel G2 structure. Okay, so this is saying that the links of spin 7 cones admit nearly parallel G2 structures. and the metric is the same. Okay. Now, from this proposition, together with the fact that manifolds that have holonomy contained in spin 7 are Ricci flat, it immediately follows that if phi is nearly parallel, then the induced metric has to be an Einstein metric with scalar curvature equal to 42 in this case. That's because it's a general fact that if I have a Ricci flat cone, then the link has to be a positive Einstein metric. So even aside from applications to holonomy theory, nearly parallel G2 structures are automatically Einstein, and people are very interested in Einstein manifolds. So they're interesting for this reason as well. Okay. Now, in this proposition, we had the holonomy group just had to be contained in spin 7. Now, spin 7 has several subgroups which can be holonomy groups, and this gives us a sort of a kind of a rough classification of nearly parallel G2 structures, depending on what the holonomy group is. So if the holonomy group of the cone metric is actually contained in sp2, then M, which will be nearly parallel in this case, is called a 3-Sasakian manifold. If the holonomy group is contained in the larger group sq4, then M is called a Sasaki-Einstein manifold. And then finally, if the holonomy group is actually completely equal to spin 7, then M is called a strictly nearly parallel G2 structure. So we sort of have this chain of possibilities for the holonomy group sp2, which is a subgroup of SU4, which is a subgroup of spin 7. So this is sort of the holonomy group of the cone. And then this is sort of what M is called. So M is called 3-Sasakian. In this case, Sasaki-Einstein. In this case, and strict if it's equal in this case. Okay. Now, luckily, there are homogeneous examples of these structures, of all these various types. And in some sense, the homogeneous examples might be the most important examples, because when you think of the most simple conical singularities for spin 7 manifolds, you might hope that the link should be close to a homogeneous manifold. So the simplest example is the round 7 sphere. So you can present the round metric on the 7 sphere as a metric which is homogeneous under an action of spin 7 on the 7 sphere, where the stabilizer is G2. So you can get a spin 7 invariant nearly parallel G2 structure on this manifold that induces the round metric. And in this case, the holonomy of the cone, well, the cone turns out just to be R8 with its flat metric. So the holonomy of the cone here is trivial. So this example is 3-Sasakian because the holonomy is trivial, which is a subgroup of sp2. Another interesting example is the so-called squashed 7 sphere. So here you can present S7 alternatively as a homogeneous space as the homogeneous space sp2.sp1 mod SO4. And it turns out that this space presented this way carries a sp2 sp1 invariant nearly parallel G2 structure that induces an Einstein metric on S7 that is not isometric to the round metric. Instead, it's isometric to Jensen's Einstein metric on the 7 sphere. So what's happening here for the geometry of this metric is that you sort of have a fibration, the Hopf fibration, the quaternionic Hopf fibration, S3 to S7 to S4. And you can consider a 1-parameter family of metrics by squashing the fibers of this. So you're changing the metric on the directions that point in the fiber direction. This gives you a 1-parameter family of metrics, and there's a particular value of the parameter, which gives you an Einstein metric. And it turns out that this Einstein metric is induced by a nearly parallel G2 structure on the 7 sphere that is different from the nearly parallel G2 structure that induces the round metric. That gives you the squash 7 sphere. In fact, this situation, and this metric on the squash 7 sphere turns out to be a strictly nearly parallel G2 structure. This situation with the 7 sphere generalizes to all 3-Sasakian manifolds. So on any 3-Sasakian manifold, there is a fibration by 3 manifolds. And if you alter the metric on those, you can obtain a second nearly parallel G2 structure, which will be strictly nearly parallel. Okay. Another set of examples come from the Adolf-Wallach spaces. So these are 7-dimensional manifolds that you get by quotienting SU3 by a circle subgroup. And the circle subgroups here are indexed by coprime integers K and L. So you get so a whole collection of different manifolds, infinitely many different manifolds, and these all admit nearly parallel G2 structures. Okay. Another example is the Stiefel manifolds. This was S05 mod S03, where we think of S03, say, just embedded in the standard way. So as the group that fixes two directions, gives a standard embedding of S03 inside S05. And this homogeneous space is a Stiefel manifold, and it admits a Sasaki-Einstein metric. Okay. The final homogeneous example I'll talk about is the Berger space, which is the topic of this talk, which is the space S05 mod S03. But unlike in the Stiefel manifold case, this S03 is a non-standard embedding into S05, so it's not conjugate to a copy of S03 that fixes two directions. It's actually conjugate to an S03 that acts irreducibly on R5, and we'll talk about that when we get to the section about the Berger space. Okay, so this is sort of an overview of the homogeneous examples of parallel G2 structures. Okay, the next thing that we have to talk about is associative submanifolds. So if I have a manifold with a G2 structure, then I can look at what happens to oriented 3-dimensional submanifolds. So an oriented 3-dimensional submanifold N, say, of a manifold M that has a G2 structure phi, is going to be called an associative submanifold if, when you restrict the 3-form phi to N, it turns out to be equal to the volume form on N. Now, you get a volume form on N because, M emits a Riemannian metric, so we can restrict the Riemannian metric on M to N and look at the volume form there. We're asking that volume form be equal to phi restricted to N. So this is a non-trivial condition on the 3-dimensional submanifold N. There are two particularly interesting cases, depending on what we can say about the G2 structure phi itself. So the first case is that if phi is what we call a closed G2 structure, so that d phi is 0, then phi defines what's called a calibration. And in this case, associative submanifolds will be calibrated submanifolds, and that actually forces them to be volume minimizing in their homology class, which is a very interesting property. So when the G2 structure is closed, you get that these associative submanifolds are minimal submanifolds because they satisfy an even stronger condition that they're volume minimizing in their homology class. Now, in our talk, we talked about nearly parallel G2 structures which are not closed, but it turns out that if phi is nearly parallel, then the cone over N is a Cayley submanifold of the cone on M. So we said that the cone on M had a spin 7 structure. Had a metric that had only contained in spin 7, and it turns out that that means that there is a 4 form on the cone on M, and it turns out that that 4 form will be closed. And if we have an associative submanifold of the link, then the cone on that will be a 4-dimensional submanifold of the cone on M. And it turns out that that actually will be a calibrated submanifold for this calibration. This thing is called the Cayley 4 form. So the cone is calibrated by the Cayley 4 form. That's what a Cayley submanifold is. So the cone over N turns out to be a minimal submanifold of the cone on M, and actually that forces N itself to be a minimal submanifold of M. But it doesn't follow that N is going to be volume minimizing in its homology class. So all we have here is that N is just going to be some example of a minimal submanifold of N. Okay. So the motto here is that associative submanifolds of nearly parallel G2 structures will give us models of conically singular Cayley submanifolds. And again, conically singular Cayley submanifolds, that's something that you would be interested in that appears naturally somehow in the theory of exceptional Holonomy manifolds with Holonomy spin 7. So this is sort of the motivation for studying these associative submanifolds in nearly parallel G2 structures comes from this. It's also interesting because these give examples of just minimal submanifolds of higher codimension inside Einstein manifolds. And that is itself also inherently interesting. I'll also say that there's a program initiated by Donaldson and Segal to construct invariants of G2 structures And the way you build this invariant of a G2 structure is that you want to count the associative submanifolds. Should be possible to count those in some way, and also count gauge theoretic objects called G2 instantons. And if you somehow match the counts correctly, they should together form an invariant of the G2 structure. So this is kind of lingering in the background as motivation, because although you might want to apply this invariant to the case where the manifold has holonomy G2, it's sort of expected that you're going to have to widen your scope away from manifolds with holonomy G2 just to general G2 structures. And then it's interesting just to note the sort of phenomena that can occur for associative submanifolds in sort of general G2 structures. Okay, so that's kind of lingering in the background as motivation as well for our study. So that completes our background on G2 and associative submanifolds, etc. So now let's talk about the Berger space itself. So I did mention it a little bit before, but now I'll say exactly what it is. So if I think of the vector space R5 as the space of, say, symmetric traces 3x3 matrices, if you count that up, that will be 5-dimensional. So symmetric matrices, that's 6 dimensions, and then traces, that takes away 1 dimension, so you're left with a 5-dimensional vector space. So I'll call that sim20 of R3. So, now the action of SO3 by conjugation on these matrices gives us an action of SO3 then on R5. And this gives rise to a sort of a non-standard inclusion of SO3 inside SO5, okay, via this action. And this SO3 acts irreducibly, so this inclusion really is not the standard inclusion whatsoever, because it's different, gives you a different representation. Now the Berger space B is going to be the resulting homogeneous space where you take SO5 and you quotient it by this non-standard SO3 that lives in there. Now the Berger space, I think it's a really interesting example of a 7-manifold. It has a lot of interesting properties. So some of those are, if we decompose the Lie algebra SO5 with respect to the action of this copy of SO3, it splits into a copy of SO3, which you expect, and then the remainder is the space H3, which is the space of homogeneous harmonic cubics on R3. Okay, that's a 7-dimensional vector space. So this H3 is the isotropy representation of B. And so this isotropy representation is irreducible. So B is itself an isotropy irreducible space. And that's relatively rare. That doesn't happen all that often, really. So that's an interesting property. Another interesting property is that the homogeneous metric on B. So isotropy irreducible spaces have up to scaling a unique homogeneous metric. And this homogeneous metric on B has positive curvature. So I think this is the first appearance of the space B, was in paper by Berger, where he was looking towards the classification of homogeneous metric with positive curvature, and this space appears here. And again, there aren't that many of spaces, homogeneous spaces with positive curvature, so B also appears on this list of spaces. It's interesting. And topologically, B is a pretty interesting space as well. So it turns out that, like S7, B actually turns out to be an S3 bundle over S4. Okay, but B is not diffeomorphic or homeomorphic to S7, but it is a rational homology sphere. So its homology over Q is the same as homology over Q of S7. So in some sense, B looks a little bit like S7 in some ways. Okay. So we're interested in B because it carries a nearly parallel G2 structure. So it turns out you can do some representation theory to say what are the SO3 invariant 3 forms on the vector space H3 that we talked about before. It turns out there's a unique one up to scale, and then if you translate this around B, you get a unique SO5 invariant 3 form phi on B. And it turns out that this 3 form phi has the right algebraic properties to define a G2 structure. And it also, it turns out, defines a strictly nearly parallel G2 structure on B. So our Berger space B carries one of these strictly nearly parallel G2 structures, which we talked about in the previous section. Okay, and actually B plays an interesting role in sort of the history of manifolds with special holonomy, because it was the first known example of an explicit metric with holonomy group equal to spin 7. So this example appears in Robert Bryant's sort of paper Metrics with exceptional holonomy, which sort of restarted the theory of exceptional holonomy. and it appears as sort of the only explicit example there that has holonomy group equal to spin 7. So it appears right at the start of the history of the subject. Okay. Now, as we said before, the metric induced by a nearly parallel G2 structure is automatically Einstein. And that's obviously the case then for this metric as well. So our metric G phi is Einstein. It would also be possible to see this by the fact that this three form is S05 invariant. So the metric that it induces must also be S05 invariant. But B is isotopy irreducible. So there's a unique up to scale S05 invariant metric, which so they must agree. And it turns out then that also the metric on an isotopy irreducible space must also be Einstein. So you can also see this fact by the fact that B is an isotopy irreducible space. Okay. So our definition of B was perfectly reasonable, just some homogeneous space, but it's not especially good for sort of thinking about B concretely. And it's not especially good for somehow for thinking about submanifolds, it's not as useful. So the next thing that we'll talk about is an explicit realization of B, really as a sort of a set of objects acted on by S05 with stabilizer S03. So we'll think of B as a space of certain surfaces in S4. So we'll start by saying, I can think of S4 as the unit sphere inside the space of symmetric traceless 3x3 matrices. And inside that sphere, I can consider the subset of matrices that consists only of matrices that have a repeated eigenvalue of half. So these are the matrices that are going to be conjugate to the following matrix: half, half, minus 1. So the matrices that are conjugate to this thing. Okay, and this defines some SO3 invariant subset here. Okay. And this subset, it turns out to be, it's an SO3 orbit. It's not just SO3 invariant, it's just a single SO3 orbit. The stabilizer is O2. So this subset is a copy of RP2 inside SO4, which we'll call the standard Veronese surface in SO4. Sorry, the standard Veronese surface in S4, the 4 sphere. Okay, and then we'll make a definition. And we'll say that just in general, a Veronese surface is a surface in S4 that's SO5 equivalent to the standard one. Okay, so SO5 acts on S4 and it pushes around this surface sigma 0. And I'll just say a surface is called a Veronese surface if you can push it to be the same as sigma 0. Okay, and then our proposition is that the Berger space B is diffeomorphic to the space of Veronese surfaces in S4. Okay, so we can really think of the points now in our space B as being themselves surfaces in S4. Okay, these Veronese surfaces. And the proof is really not so hard. So it turns out then that we have a natural SO5 action on the space of Veronese surfaces just by virtue of their definition. And it's not too hard to show that the SO5 stabilizer of the standard Veronese surface itself is that copy of SO3 that we were talking about before. So that immediately gives you the result that the space of Veronese surfaces is SO5 mod SO3. Okay, but this realization is really useful because now we can really think about points, say, or submanifolds as B as being like families of surfaces in S4, and that gives us a much better geometric picture of what's going on. Okay, so we can now kind of get on to the main part of our talk. We've given all the background where we want to discuss associative submanifolds of B with respect to its nearly parallel G2 structure phi. Okay, and in general, you need an idea to study these things. The local theory is well understood. There'll be lots of local examples, but we're interested in global things. And what we do is we impose two kind of geometrically interesting conditions and then study the submanifolds that satisfy these conditions. So the first is we study ruled associative submanifolds. And the second is we're going to study associative submanifolds that have special Gauss map. Okay, so we'll begin with the ruled associatives. So to give a bit of background, if you're studying submanifold theory, then a very natural condition that you might want to impose on a submanifold is that it be ruled, or it's the same thing as foliated, by some special class of curves in the ambient space. So you know, in the theory of surfaces in R3, you're often interested in the surfaces in R3 that are ruled by straight lines. Again, that's a very natural condition. So they through each point of your surface, this point is contained in a line which is contained in the surface. Okay, well, this idea of ruled submanifolds has been studied in calibrated geometry before and special element before by, say, Robert Bryant, Fox, Lote, and Joyce. And they studied ruled calibrated submanifolds of Euclidean spaces and spheres, say. So you can take, say, R7 together with standard 3 form, V0, the standard teaching structure of V0 that we defined. And you could say, for example, study associative submanifolds of this space that were ruled by lines. That's the kind of thing these people studied. Now, in those cases, like I say, the ruling curve choice in a Euclidean space or a sphere, there's some very natural curves which are given to you, which it sort of makes sense to consider as possible ruling curves. So the lines and circles, say. What we want to do is we want to apply similar techniques to study associative submanifolds in B, but we have a bit of a problem at first glance because there are no like immediately obvious replacements for lines or circles in B because it's a more complicated homogeneous space. So the first thing we need to do is determine an appropriate class of ruling curves. Okay, and this is done in the following way. Our class is going to be called the class of C curves. So as I said before, B, we think of it as the homogeneous space S05 mod S03. Well, then the isotopic representation of that turns out to be the space H3, which is a space of homogeneous harmonic cubics in 3 variables. Now, the action of S03 on this space is interesting. And in particular, it leaves invariant this cone of harmonic cubics that are the harmonic parts of perfect cubes. So we have a map, say, from the space P3. And this would be the space of homogeneous polynomials in 3 variables. And there's a projection down onto this space H3 that we have here. And what we're interested in is you take any sort of perfect cube here and then just map it to the harmonic part. Just take the harmonic projection down here. And then if you look at this map as you look over, as it varies over, if you take the image of this map over all perfect cubes, these things x3, x cubed, y cubed, z cubed, etc., then what you get, it turns out, is a cone of harmonic cubics that are themselves the harmonic parts of perfect cubes. So you get sort of at, so in H3, you get the space C inside H3. And this is S03 invariant. Because this map itself here is S03 equivariant. So the image you get is going to be S03 invariant. Okay. Now you take this S03 invariant thing, say at the tangent space identity, and you translate it using the S05 action. And what you get is an S05 invariant subset, which we'll call curly C, of the tangent bundle. So at each tangent space, we have a sort of a cone. In each tangent space, so we get sort of a cone bundle. That's the sum bundle of the tangent bundle. Okay. Now our definition for our ruling curves is going to be a geodesic in B. It's called a C curve if it is tangent to C. So if at every point its tangent vector lies inside this subset C of the tangent bundle. Okay, and these are going to be our ruling curves. So it turns out that these things provide an appropriate class of ruling curves for associative submanifolds. Probably the best way to understand them is to think of them in terms of our description of B from before as a space of very nice surfaces. And that's what the proof of this proposition will get at. So it turns out then that the space of C curves is diffeomorphic to this flag manifold S05 mod T2, so S05 mod of maximal torus, which can be identified with the Grassmannian of 2 planes in the tangent bundle of S4. So this space, the Grassmannian of 2 planes in TS4, that's a bundle over S4 whose fiber is the Grassmannian of 2 planes in each tangent space. This thing's in 8 manifolds. So we have a point in S4, and then we have a 2 plane in the tangent space at that point. Okay, and our space of C curves is diffeomorphic to this space. Okay, and the proof is not so hard. This is a sketch of a proof rather than a full proof though. Let's let pi from S05 to B denote the coset projection. Then it turns out that the C curve through sort of pi of E1 through E5, so in the direction of E1 through E5, turns out to be the set of all Berger surfaces, sigma, that have the first vector E1 should be in sigma, and then the tangent space at this point E1 should be the span of E2 and E3. So here we're thinking of this E1 through E5. This is an element of S05, so we're thinking of S05 as being a matrix. These E1 through E5 are the columns of the matrix in S05. And you just have to do a calculation involving the definition of C here to see that the set of Berger surfaces is exactly you want E1. Now that's a column vector. So E1 itself is an element of S4. Well, you want E1 to be in sigma, which is a subset of S4. And then you want the tangent space at E1 to be this span, E2, E3. And this is a point in the Grassmannian of two planes at T, E1, S4. And so this gives you the map that you want that goes from a C curve to a point in the flag manifold. And it turns out it's a diffeomorphism here. Yeah, there's a slight subtlety really. This should say the C curve through pi of E1, E5 kind of in the direction. In the direction E1 for E5. Because there may be multiple C curves through a single point, but we want to somehow say that the E1 through E5 are telling us the direction. All right, this gives us the map. So the way to think of C curves, a C curve consists of a one parameter family of Berger surfaces that all share first order contact at a particular point. So they all have a point in common and a tangent space in common at that point as well. And this is our nice C curve. So these C curves have a very nice geometric interpretation in terms of Berger surfaces. Okay. Now we want to study now associative submanifolds of B that are ruled by these C curves. Well, the way to do it is just to first say, in general, if I have a surface in the space of C curves, so a surface in GR2 TS4, that's a two-parameter family of curves in B. So that two-parameter family of curves in B should give rise to a three-dimensional submanifold of B. Because it's a two-parameter family of curves. 2 + 1 is 3. Should give you a three-dimensional object on the right-hand side. So we'll call that gamma of S, where S is the original surface. And then the kind of natural question that you want to ask is, under what conditions, if at all, what conditions can we put on S to make sure that gamma of S is an associative submanifold of B? So right now, gamma of S, if you put no conditions on S, there's no reason to expect it should be associative. But you might hope that the condition that it be associative should have some nice reflection as a condition on a surface S in this Grassmannian of two planes. Well, this question is answered by our theorem. This is, that says that there's an S05 invariant almost complex structure J on this Grassmannian space, such that any C-ruled associative in B is locally the gamma image of some J homomorphic curve S. Okay, so the answer to our question is that S should be a J homomorphic curve for this almost complex structure J that we construct here. And then so there's a converse then for each J homomorphic curve S in this Grassmannian space. There's a dense subset S0, say, inside S. So the gamma of S0 is a C-ruled associative submanifold of B. Okay, so really the answer to this question is that S should be a J homomorphic curve for this almost complex structure J. Now this theorem has subtlety in the end here. We have to restrict to this this dense subset. And that's because I told a bit of a lie here, actually. When I say it gives rise to a three-dimensional submanifold, you have to be a little bit careful because there's ways in which this construction could go wrong. But part of the theorem is saying that actually when you have a J homomorphic curve S, this doesn't go wrong on a dense subset. So it's really somehow a nice situation. This should really be an open dense subset. And even better, this open-dense subset is the complement of the zero set of a real analytic function on S. So it's kind of the nicest type of open-dense subset you can get, really. Okay, but the theorem is nice then. So it somehow reduced the problem of constructing ruled associatives in B to the problem of constructing J homomorphic curves to this almost complex structure J. Okay, now unfortunately, the J that we construct is not integrable. So we still have to, it looks like, face the problem of constructing sort of globally defined, almost, globally defined J homomorphic curves in this space. But actually this space, this Grassmannian space is quite nice because it's S05 mod T2, and our almost complex structure J is S05 invariant. It turns out there's actually quite a lot you can say about the J homomorphic curves. So we are still able to get like a nice existence result, and you can say more even. So our theorem then is that there exist infinitely many diffeomorphism types of immersed, and these will be generically one-to-one, associative submanifolds of B. So we're able to use our result to say that there are really lots and lots of immersed associative submanifolds in B, and there's all sorts of topological types. There's infinitely many diffeomorphism types here. So I'll give a sketch of the proof of this. So it turns out that something called a superminimal surface, S, in the 4-sphere, you can lift it to this Grassmannian space in such a way that it turns out to be a J homomorphic curve. And in this case, actually, you can ensure that this open-dense set is actually the whole surface here. So the construction in this case will give you really gamma S will really be kind of associative on the whole of S. So then what you want to do is you want to say, how can I construct these superminimal surfaces? Well, Robert Bryant, in a paper in the 1980s, he showed actually that any compact Riemann surface can be embedded in S4 as a superminimal surface, which is great because then you have any possible Riemann surface you can do this construction to, and you're going to get some immersed associative submanifold that's a circle bundle over this Riemann surface. So in that way, you get infinitely many diffeomorphism types of associative submanifolds here. So the kind of the picture of what's going on is you have S inside S4. Well, over S4, the space GR2, TS4 is a bundle over S4, and you can lift F, just take, say, the tangent, lift here, and that'll give you a superminimal surface. Or you could also say, for example, take the normal lift as well. So there are several different ways to lift a superminimal surface to a map here, and it turns out that one of these ways really gives you the J homomorphic curve that you want. You get this condition that S equals S naught in this case. So you get lots and lots of associative submanifolds this way. Okay, and there's a bit more you can say about these things, but somehow this theorem is kind of the main results that you get lots and lots of associative submanifolds. I should say in general, it's hard to construct associative submanifolds because you're solving like quite a complicated PDE system. So anything that you can do to construct global examples is very good. The last thing I want to talk about, and I'll talk about it quickly, is our second condition. It's these associatives that have special Gauss map. So I first have to define the condition of having special Gauss map. Well, I'll start by saying that you can take an associative submanifold that's say N3 inside B, and you can look at its Gauss map, which would be the map G, which would map into the Grassmannian of 3 planes inside the tangent bundle of B. Okay. While B is homogeneous under the action of S05, so you can always act by an element of S05 to pull it back so that you're actually in the tangent space at the identity coset of B. So remember, the isotropy representation is the representation H3. So you can take this G actually to map into the Grassmannian of three planes in H3, but at the expense of you have to only consider it up to the action of SO3, because when you translate back to the identity coset, well, you can do it in several different ways. You can do it in an SO3's worth of different ways. So this sort of gives rise to this ambiguity in the image, which you can get rid of by quotienting by SO3. So it goes into the space of SO3 orbits on this space. Well, if you assume that N3 now is associative, then you're going to map into the associative Grassmannian. So you're going to have a map from N3 into the Grassmannian of associative three planes in R7, quotiented by the natural action of SO3 in this example. Now, unfortunately, this SO3 action on the Grassmannian is non-transitive. It's quite complicated, which makes sense. The associative Grassmannian itself, this thing is 8-dimensional, and SO3 is 3-dimensional. So somehow you expect the image to have 5 dimensions, and it turns out to be quite a complicated space. But we can focus on somehow the interesting points of this space where you have like an extra stabilizer. So I'll say that the generic associative three plane in TPB will have like trivial stabilizer, but you can actually have larger stabilizers. So our definition will be, we'll say an associative submanifold N in the Berger space has special Gauss map if all of its tangent planes have a non-trivial stabilizer G in SO3. So this is sort of like a condition on the tangent planes of N, and you're asking them to lie in these special SO3 orbits on this space, here. So this is a first order condition. Because we're asking for some condition on the tangent planes of N. Okay. Now, in general, in the more simple setting where you have, like I say, a submanifold of Euclidean space, there just are no interesting first order conditions because, the group say SON acts transitively on the N planes, on the K planes. So there are no interesting first order conditions. But because B is a sort of a more complicated homogeneous space with like a smaller denominator, you do get interesting first order conditions, and this special Gauss map is somehow the most natural of those conditions in some way. So what we do in our work is we classify the associative submanifolds in B that have special Gauss map, for which the stabilizer G, we have to restrict to the case where G contains an element of order greater than 2. So that the case where you have only elements of order 2, say, turns out to be pretty complicated, so we ignore that case. But we're able to, aside from that case, classify all the associatives that have special Gauss map. So you get the interesting things occurring, like you see the examples that are ruled appear, but you also see some other interesting examples. In particular, you get a number of interesting homogeneous examples appearing. And I think the most interesting one is you get a example that has the topological type. It's a homogeneous associative that's diffeomorphic to the Poincare homology sphere. It's kind of an interesting example. This classification theorem, there's a couple of different cases, so I figured I just wouldn't talk about it in too much detail. But really what you do is, you go through group by group, and you get a couple of examples in each case, and then sometimes you get an infinite family, etc. But if you're interested, you can look at the details in our paper. I think the introduction contains sort of a full description of the classification. Okay, so that's me done with the talk. Thanks for listening, and I'll stop it there.